Series will be a very long series of nyquist. So I'll just start off with intro to frequency responses and why we need to study nyquist, and then how nyquist relate to root locus, and then so on and so forth, as you can see. So after which, all these things is just all the information you need for nyquist, and with this information, then you can start to do some one example questions. So later I'll just do it, but it'll be a long video, as I say. So I'll just start off with the thing. So the frequency response of a system is defined as the steady state response of a system to a sine wave. Okay. So what does it mean? Okay. So let's say your input, right, is maybe I should, okay, hold on a while. This red color is the input. Okay, it's the input sinusoidal wave. As you can see in the block diagram, it's a sine omega t. Okay, with a certain frequency, as you can see, it's omega. Right. So if you were to input into a transfer function, let's say some transfer function gjw, okay, you have a output of certain magnitude, an increase of magnitude, okay, and a phase lag. Then I'll just show you an example. So what it means is that in a steady state is that when it comes in, there's a transient stage over here, you see. And the transient stage, it transit into a steady state. As you can see, it's all constant now, not drawn to scale, but rather than it is supposedly like that. I mean, yeah. So this is the transient stage that I'm talking. I mean the steady state that I'm talking about. So what it means is that the frequency response, which is these responses, okay, these responses, is defined as a steady state response of the system to a sinusoidal input signal. The sinusoidal input signal is the one that is input, if you were to compare with the input. Right. So definitely, as you can see, there may be some lagging. Okay, this input is faster than the output, as you can see. So this is the so-called delay. Then I'll just show you a little while. So and then yeah, so this is the phase, which is the delay, the phase angle. We often call it a delay actually. So let's take a look in the MATLAB. I actually plotted it up. So when we have a transfer function. Before I start, why is JW is because we change s equals to JW, j omega. Okay, so typically if you remember your transfer function is always g of s, right? So since s is equals to j omega, and therefore gj omega. So this is the transfer function in terms of frequency. Okay, so this is just I just want you to know. And then okay, so this is the transfer function 1 over s squared plus 5s plus 7, as you can see, although it's not very big. Okay, so as you can see over here, maybe I just change it to amplitude of 1 first. So if I have an input signal, sine wave, okay, and a gain and a transfer function, and then I compare it with a sine wave, the same sine wave, okay, I just wanted to show you the input and the responses of the transfer function, so we can see both things at once. But let me show you the initial input first. Okay, so the initial input, I put it is 0.5 amplitude. So as you can see, if I run it, you should be able to see that it is 0.5 amplitude. Right, it's about 0. If I had to zoom in, okay, sorry, I didn't zoom in. Where's the zoom in? It is a 0.5 amplitude, as you can see, right, from 0 to 0.5. So this is the sine wave, the input sine wave. Okay, so now let me switch it to here. Okay, so I run. As you can see, this is the input sine wave. Sorry, this purple color is the input sine wave. Sorry, so it's different from just now the yellow color one. So this is the input sine wave of the purple one. Maybe I should change it to one whole. Okay, this is exactly the same as just now that one. Okay, the yellow color one. When I put it into here first. So if I were to look into just the input only without any transfer function, your sorry, your sine wave is actually this in this manner, right? 0.5, right? This is your initial signal without any distortion or any transfer function within it. So if I were to put it with the transfer function and compare, so let's say I have a gain in the transfer function. In this case, gain is equal to 1, so there'll be okay, hold on. So I just run it first. This is the initial signal, and then when go through the transfer function, this is the purple color one. As you can see, it is the amplitude isn't that large. Alright, so the transfer function actually minimize the the signal. Okay, as you can see, the purple color minimize the signal. So what I can do over here is that I can increase the gain. Okay, let's take a look in the zero gain first. See what will it be. As you can see, the zero gain. Okay. The zero gain has a little distortion. I don't know why. Okay, hold on a while. Okay, so you can see zero gain. Okay, don't care about this squiggly lines. This is just sine wave, but I don't know why. But the responses, as you can see, is 0 because you actually set the gain equals to 0, so everything goes to 0. Okay, so let's take a look if we have a transfer function of gain 3. Okay, let's increase the gain to 3 first. Let's see how. As you can see, when I increase the gain, you have a slightly higher amplitude. Okay, so my purpose is to maybe hope to reach 0.5. So maybe I could get it into 5 first. It's almost there, as you can see. It's almost there. Maybe I should add in 7. Okay, it's about there. Maybe I should add in about 8. 7.5 in. So it's about there, as you can see. As you can see, once I reach it in that manner, you can see that my there's a phase angle, there's a phase shift already. You see, although the sine wave it still holds the sine wave. Okay, it still has the sine wave trend, but as you can see, it is there is a angle with there is a phase lag. As you can see, there's a phase lag over here. This point, this peak and this peak to peak point, okay, this peak and this peak, there's a difference. So the input is faster than the output. So if you were to calculate in some manner, I also don't know how to calculate, but you have the degree, you have a phase angle, this data over here. Okay, so this is generally the concept. So so previously was the second order. Okay, second order system and first order system is always stable. Later in the back we'll go through. But just remember that first order and second order system are always kind of stable. Now if you introduce a third order system, as you can see, we have a different transfer function as this. Previously was this one. Okay, now I have this one. As you can see, the after I run, okay, I've already clicked run. So if I run, okay, where am I? Great job. Okay, hold on a while. So if I run this thing, as you can see, the input is still the yellow color, right? Okay, 0.5 amplitude throughout. As you can see, there is a a little unbalance in here and there. You see, but as it moves to somewhere about 60 seconds, 1 minute, it actually start to get a little stable up to this point, as you can see. From here, you can see there is a ups and down, and then up to about here, you can see that the wave is kind of stable now. Okay, so this, as you can see, the gain is 7.5. So I just use the one. So as you can see, this transfer function requires more gain because it has more system in there. So you certainly have more lags. So if I increase to gain 10, okay, what do I have? Okay, I still almost there. I still can't reach that typical as you can see, the steady state over here it's still low. So maybe I could get it to 16. What would it be? Okay, my system is still a little unstable. It's very unstable now, but it will still goes back to the transient stage. Yeah, I should put it in the 20 first, and then I run it with a time. Hold on, and then only hold on. I just put it a more time, maybe 300. So I just run it again. Now this time needs a little time, I think. Yeah, 300 requires a little more time, I think. So you pause a while, hold on. Okay, so in order to show you the okay, I didn't cheat your feeling, okay? So this is my trans. This is when I add in a gain of 20, okay? This is when I add in a gain of 20. What I get is this. As you can see, at this very first few part, it's kind of like unsteady. Up to about this point, okay, this is still a little peak, right? Up to this point, about 100 seconds, okay? About 100 seconds plus, you can see that it goes to transient. So overall, it will still goes to steady state. Okay, overall it will still go to steady state. This is the thing. So as you can see, when you increase the number of order, you're actually introducing more instability in there. So the instability, as you can see, is over here is it's this all this stability. So what if I add in a bigger transfer function? Okay, so I have a very big chunk of transfer function. Okay, so I just put it here, and then I just slot it in. So okay, if I run it, what do I get? Okay, as you can see, the system goes straight away KO. You know, maybe I should run in again one. So let's see how it goes. You see, my scope is already done. It's already spoiled. So maybe I should run again. As you can see, even if I set it to 1, at first if I set this gain to 1, you can see that the system is so unstable. You see, when it starts to go up okay, and then suddenly boom, it goes very unstable. So this as your this one increases, your transfer function increases the order. It is very dangerous. Maybe I should try a smaller gain, see how. You see a smaller gain, at first the smaller increase, but it will still goes to, you know. So this is very undesirable. So therefore this is why we are looking in things. But however, as you can see, maybe I should pause a while. So that I just replace back the second order system, okay, with a 7.5 gain back, okay. What we have here back here is the so-called our, maybe I should zoom in a little. It's a little phase lag, right? So in this case, you don't know how the phase lag would have, right? You don't know how to calculate. This is pretty tough. And then the amplitude wise is okay. It's mainly on the gain part. But what the nyquist plot is actually trying to plot, okay, the polar locus, which is also the nyquist plot, is actually to plot against certain issue with stability and phase angle. So as you can see, this is the phase angle. So as you can see like that, how you want to calculate? Okay, you have to find I mean the peak to peak point 14 to 16. I mean 14 to about 14 point something, and then you, I don't know. So basically this is the key concept I just want to convey in intro to frequency responses and why we study nyquist plot. And then later I'll just relate it to root locus. Okay, how does nyquist plot relate to root locus? So I'll see you there.